before the commencement of today's class, we would like to pick it up from where we stopped. Those of you that were in last class, can you signify? Alright, I give you assignments, give you some questions. So the motive of the question was to prep you guys for what we're going to be doing today, and I hope it did its work. So I gave you some set of questions, like about, it's not 10 also. Is it not 10 also? Was there any calculation question? No calculation question. Alright, upstand.
Stand up as you just said.
Upstand. Okay. Alright, the first question, I said sound travels faster in steel than air. Is that true or false? In air, I gave you in air and in steel. Is it true or false? Why?
Because of sound travels faster in steel than
air. Why now?
because like there's
Give me a theoretical explanation. Also, I say, I'm speaking English. Give me something to back your answer. Thank you.
What did she say?
Yes, I like that. Sit down. You are. Sit down. That's beautiful. You are not in the last class. Please sit down.
In the last class online.
Online, even online.
Alright, I said sound is a mechanical and transverse wave. True or false?
False.
Why is it false?
Because it is mechanical.
Mechanical in the sense that what?
It needs a medium for it to travel.
Okay. Then transverse in what sense?
It's not longitudinal.
It's longitudinal.
Yeah.
Why is it longitudinal?
Travels parallel to the sort of.
So what's the answer now?
The answer is false. Because of its mechanical constitution.
Okay, I'll sit down. Yes, now she said the most.
Hey.
You're just backing from afar. I said sound can be reflected, refracted, diffracted, and polarized. True or false? True.
Yeah.
Why is it true?
It can be reflected. It can be echo. That is echo.
Alright.
It can be refracted. It can change direction.
Okay.
Diffracted. It can be diffracted. And polarized. Yes,
I was waiting for that polarized. Who gave you that sound can be polarized?
It's not transverse. It's not transverse that can polarize.
I see your focus. So, polarization is not a character.
Flow said sound is a mechanical wave.
Yes.
Blooming Flow said this is secret. Okay, for lesson. That's crazy. That you show us your student.
What's that she rocking at
Alright.
No, it got me.
So, polarization, like I said, is attributed to just and most especially what? Light. You are all right. Moving on. It said sound can be produced only by a vibrating object. True or false?
False.
Why is it false? Why is it false? Yes, tell me, why is it false?
When we talk, is sound and are you an object?
No, we are
Vibrating.
vibrating.
Yeah.
Oh, you don't know the phenomenon behind voice production. It's vibrational.
No.
So you can sit down, baby. Come on, why? So, it says sound can be transmitted through any material substance, whether gas, solid, or liquid. True or false?
True.
Why is it true? Yes, now. Why now?
If you like do be vibration and sound and gas like the air and
Okay. This person said it is not possible to have class on Sunday. Physics class on Sunday. You now said this is crazy. You show us your student. Why?
Hello. One class. One class. So, is that your own explanation?
That's only like
How do you think the shark detects its prey inside water?
shark.
Ripples, correct? One more thing. Vibration. It's very sensitive to vibration. Then, for solid, definitely sound can be transmitted through solid. Then, gas. Let's use air. Air.
I say it now.
So true is the answer, Abby. All right. Moving to the next. I'm done now. As a sound is a longitudinal and electromagnetic wave. True or false? Which one is not there?
Magnetic.
And why is that?
Because it cannot travel through vacuum.
Yes, sound requires a material medium for its propagation. All right. What else? Oh, internet is down. He said it was. Why haven't read the question? Okay, sound cannot be propagated through a vacuum. True or false?
True.
Yes, ma'am. No.
All right. 6. Sound travels faster in cold air than in hot air. True or false? Why? Why is it false?
When they eat now,
The degree of temperature does not matter. That is wrong.
Someone said, say, I, if you are from Acada Ace.
All right. The reason why it is false is because hot air. You know kinetic theory of matter, right? So in hot objects, what tends to happen to the molecules of the particle? Collision. So they tend to what? Move faster, right?
yes.
Then in cold air, what happens? There is what? Slower collision. So now, in that sense, Which one do you think will produce will allow sound to pass through?
Hot air, because
Hot air, because there is more collision in the molecules. Do you get? That is why the answer is false. And don't tell me that the degree of the temperature does not matter, because it does. All right. Moving to the next. What's the next question?
sound travels regardless of air sound.
Okay, as the sound travels with the same speed in air, regardless of air pressure of the frequency of the sound. True or false? True or false? True or false? Why is it true? And if it's false, why is it false? Yes, I thought you guys would be curious to know the answer. You were not curious enough.
I think that you were here. You're going to explain.
Oh, I see. So the answer is true. The air pressure of the frequency of sound does not affect it, because even if the what is it called? This how do they call it? I mean, I try inside pods. So regardless of the air pressure, either the air pressure is high or low, the speed of air of sound in air remains what? Constant. So it travels with the same speed in air, regardless of air pressure. Then what's the next one? The following are examples of transverse waves. Yes, the first one, ripples on water. True or false? Transverse. True or false?
True. You use the water.
Yes, ripples on water.
True, sir.
Why is it true?
Yeah. It moves. You know that way. It moves like a wave. You put that on the hand.
It's all perpendicular, like, you know, you get, like, guys, and now, like, view.
Wait, if JAMB should ask you this question, is this how you explain?
Yes, now, view, like,
You use view.
no, like, this is the source, yeah.
Alright.
Shit.
Yeah, I thought you were explaining something.
I was explaining.
It's type sheet. It's the type sheet part of the explanation.
So, like, it's the source of the wave, and the ripple is coming like this. So the ripple is traveling, like, you know, in perpendicular direction. Yeah, type shift.
Alright, so ripples on water is true. Sound waves in steel wire. Sound wave in steel wire. Why is it false?
Why is it false?
It is false. Because it's false.
Sound wave in steel wire.
Like, you should get a jump like parallel, perpendicular. That's why it is. And I'm correct. Yes.
X-rays.
That one is true. It's true. Yes, true.
Why is it true?
Why is it true?
That's it now. Like, when you put the land body now, you show so it sounds like
So, hello, one class please. See, view that I hear on YouTube. Now, X-rays are examples of electromagnetic waves. True or false? And all electromagnetic waves are what? Simple as that. Which one is view?
See, you don't come and look, I'm right. I'm right, Sha. Come up with just.
But that view,
No, like,
extract it. So stationary waves in a resonance tube. Stationary waves in a resonance tube. Why is it false?
Because it sounds in the CY.
What example is that stationary waves in a resonance tube? It is a wave in closed pipe now. Have we?
Yes.
Yeah.
In closed pipe. You have something like this. So you have this other one coming like this. So stationary waves in a resonance tube. This is what they are talking about. And the resonance tube will be closed. It is similar to, what is it called? Closed pipe. And waves in pipe or tubes are examples of what? Are examples of what now?
Waves in pipe or
Tubes are examples of what?
pipe. Pipe.
Waves in pipes or tubes are examples of what?
Okay.
You guys are not reading.
Like, I don't get. Is it like, this should be like,
Yeah, longitudinal. Waves in pipe or tubes are longitudinal. So this answer is false.
But explain how that stuff. Should be in pipe. What are
Okay, why it is closed pipe or open pipe?
Like, why is like parallel? But what is coming like this? Yeah, where is the source coming from? It's not like, let's say.
No, I'm not even talking about water.
I know, I'm saying pipe. Oh, Jesus. But let's I'm saying that like
Any wave that will travel in any tube will travel what? Parallel. Either closed or open, it will be parallel. That is why it is longitudinal. Stationary waves in vibrating string. Yes. Vibrating string. More like your guitar. Sure. So that is that and that. So let's start. You can sit. So today we are starting with speed of sound. Speed of sound. Do you know speed of sound in air used to have a constant value, just like speed of light in air? Do you know? So you have to know the value also. You have to know the value. The speed of sound. The speed of sound depends on the medium. The speed of sound depends on the medium at which it travels. Full stop. It depends on some characteristics. Of the medium itself. It depends on some characteristics of the medium itself. And this includes one, temperature. Oh God, I said the degree of the temperature does not matter. What was the first character we outlined? temperature. Matters a lot. Till tomorrow, I'll still keep saying it. You said the degree of the temperature does not matter. And it does. Alright, the next one, pressure. 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 Then density. 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 The last one, elasticity of the medium. Elasticity of the medium. Speed of sound and temperature. Another subtopic. Speed of sound and temperature. Speed of sound and temperature. Speed of sound and temperature. The speed of sound in air. Speed of sound in air. The speed of sound in air depends on the temperature of air. Depends on the temperature of air, and it is independent of the pressure of air, and it is what? Independent of the pressure of air. That brings us back to the question I gave you for the assignment. I said sound travels with the same speed in air regardless of air pressure of the frequency of the sound, which is what? Now, are you seeing it? Speed of sound is independent of the what? Of the pressure of the air. Do you get that now? Is there any question? Alright, moving on. Full stop. It increases with increasing temperature of air. It increases with increasing temperature of air. Full stop. For every 10 degrees Celsius rise, for every 10 degrees Celsius rise in the temperature of air, for every 10 degrees Celsius rise in the temperature of air, speed of sound increases by about 0.6 meter per second. So now we said okay, the mathematical relation between V and T is that V, which is the speed of sound, is directly proportional to the square root of temperature. V is directly proportional to the square root of temperature, and if we have V to be directly proportional to the square root of the temperature, we also can say V is equals K root what? Root T. If you are removing the proportionality sign, it comes with an equals to and a constant, right? Yeah. Now, if we have 2 speed of sound and 2 temperature, that's we are considering 2 instances. Are you getting it now? So we can say from here, K is what? V over what? Square root of T, having. Now for two substances, which is K1 and what? K2, you can say this is V1, then this one is V2 over. And since K is constant, we can say V1 over root T1 is equals V2 over root T2. So this is the formula you use when you have two instances. You can put this down. Is there any question? Yes, speed of sound in air. Okay, let me write it out. Where V equals speed of sound in air, and T equals temperature.
Okay. Someone said.
And K proportionality constant.
Someone said.
Yes, sir.
You should come again. We don't know why the person said you should come again.
Alright, I'll come again.
Sir, you don't need to come again. It is live class. It is recorded. The person
okay, you can always visit again. And visit the site again.
Hi, bro. Are you from Africa?
Yes, I'm from Africa. Nigeria. Alright. So we can say T is temperature. Some people can say it is absolute temperature, and you know that will be measured in what? Kelvin. Thank you. So Kelvin. Is there any question so far? No question. Alright, I have a question for you. UTME question 25 1998. UTME right now. UTME question 25 1998. Shall we? The velocity of a sound. The velocity of a sound wave. The velocity of a sound wave at 27 degrees Celsius, the velocity of a sound wave at 27 degrees Celsius is 360 meter per second. It's 360 meter per second. Full stop. Its velocity at 127 degrees Celsius is its velocity at 127 degrees Celsius is a 120 root 3 meter per second. A 120 root 3 meter per second. B 240 meter per second. C 240 root 3 meter per second. And D 720 root 3 meter per second. So that is JAMB question 25 1998. So should we solve it together or you give it a try? Remember, convert your Celsius to Kelvin. Your temperature in Celsius converts to Kelvin. That's you add 273. So what are you getting? Yes, what are we having? scientific calculation. 240 root 3. Collect calculator from this and see what you do. 240 root 3. Alright, let's do it together. Alright, let's do it together. What are the parameters given?
V1 is equal to 360 meters per second.
V1
Yes.
equals
360.
360 meter per second. What else?
V1
T1
27.
27 degrees Celsius. So to Kelvin we have 273 plus 27, which is what, 300 K. Yes, what else?
They not give us V2.
V2, that's what we're looking for.
Yes, T2
Then T2
127 degrees.
127 degree Celsius, which is 273 plus 127, and that is what, 400 K. Applying the formula, this, so we have V1 over root T1 is equals V2 over root T2. Now we make what? V2 the subject of the formula. Abi? Cross multiply, we have V1 root T2 is equals V2 root T1. So divide both sides by what? Root T1. Divide both sides by square root of T1, and this cancels out. Therefore, our V2 is given as what? V1 root T2 over root T1. So let's input the what? Parameters, right? So V2 equals 360 times what?
400.
Square root of 400 all over
Root 300.
square root of 300. So what do we have?
360 times 20
V2 is equals 360
times 20
times 20 over.
10 root 3.
Some people cannot still understand how 10 root 3. 100 times what? 3 from your short form. So V2 is equals 360 times 20, 72 all over 10 root 3. So what do we have? So so we rationalize, have we? Rationalization of sort. So we have V2 to be equal to what? 720 over root 3 times what? Root 3 all over root 3. So V2 is equal to what? 720 over 3 root 3. Abi? This year 1, this year 240. So our V2 is what? 240 root 3 meter per second. This is our answer. Is there any question? Any question? As simple as Amala. As simple as it's because you don't know how to do it now. Ah, below, why? Oh, Jimmy, why? Kí ló wà lébẹ̀, àbí? Aṣọ see. Àwọn ọmọ Indomie generation. Alright, I hope we all understood this. Those are the extension. Hello? You got this? Alright. The next one, speed of sound and density. 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 Alright, let's put this down. Speed of sound increases with speed of sound. Speed of sound. Are we all done with this?
Yeah.
Are we all done with this? Let's give them some more time to write.
Wow. You said our speed of light is 3 So speed of sound is 0.6.
It is not. Read that sentence. Say for every 10 degrees Celsius rise in temperature, there is an increase of about what 0.6 meter per second. So that is not the speed of sound in air. You get that now? It has a value, I think 330 meter per second or so. Just check it out. Check it out. So sometimes, when do you become this? My Kaja. Ça va bien, merci.
I don't know if actually.
Yeah, they do anything. Asha ti kuku sọ̀rọ̀. It's not negotiable. Okay. Alright, speed of sound and density. Speed of sound and density. Speed of sound increases with decreasing density. Speed of sound. 343. She should be 330. Then I know the value we used then was 330. 330.
343.
Alright. Speed of sound increases with decreasing density of a medium, right? It is faster in hot medium than liquid. Speed of sound is faster in liquid than in gases. It is faster in liquid than in gases and faster in solids than in liquid. So, like a descending order. Solid is greater than liquid, right? And also greater than what? Gas. So you can put this down if you want to keep remembering. You just see this, you know the arrangement. Yeah? Only if you just screenshot it. I've always
No, like
please put it up.
No, I don't need to do it.
Oh, shit, I go for you. Oh, Sheba. We have screenshot it. Sister. So I want to throw this question. In which of the following media is speed of sound fastest? Yeah. Okay, assignments. Assignment one. You know how we used to do it now. We're not done with the class now. Don't care. Yeah, nah, assignment one. Assignment one. Is the speed, I'm asking a question, is the speed of sound, yes. Assignment one for today. Is the speed of sound affected by the wind direction?
Cool, just have a question last year.
Direction. Give reasons for the answer. Give reasons. Is the speed of sound affected by the wind direction? Give reasons for the answer. Because they shiny it to him. Because they shiny
I was
it to
thinking
him.
about something.
Closer.
No.
Someone else is
Alright. Speed of sound and elasticity. We're talking about the last character. Remember, we have talked about pressure. What did I say about speed of sound in air and pressure?
about that. Okay, it's not affected.
It is independent, of the air pressure. Alright, speed of sound and elasticity. Speed of sound and elasticity. Speed of sound and elasticity. Oh, more this noise. Speed of sound and elasticity. Tell them not on. Tell them not on.
Yes.
Speed of sound and elasticity. Ma affect class. Emma to.
I'm not sure class for me.
Oh.
What will you affect you?
Okay.
Will you affect me? Yes.
Alright.
Mute. Nice around.
Alright. Speed of sound and elasticity. Speed of sound increases. Speed of sound increases. Speed of sound increases with increasing elasticity. Speed of sound increases with increasing elasticity of a medium. It increases with increasing what? Elasticity of a medium. And it is given by, remember we did not give mathematical relation for density, Abi? So now we relate density and elasticity together. So we say elasticity all over the density. What's the name of this one? What's the name of this one? This alphabet. Your density. What's density? What's it called? Yes, the alphabet. The Greek alphabet is to represent density. Hey! It is rule.
I was supposed to say design that it has
where E is equals elasticity and rho is equals density. So you can put that down. We'll be needing it in the future.
the elasticity of
You just calm down. Alright, ultrasonic sound, another topic entirely, another subtopic entirely. Ultrasonic sound. Ultrasonic sound. Hello.
Is it one? Is that one?
ultrasonic sound. The audible frequency range of sound is between 20 Hz and 20,000 Hz. 20 Hz to 20,000 Hz. Yes, sir.
So you have 30,000 you carry 6 hours. The transfer
Wallet. No fiat. All right. The audible frequency range of sound is between 20 Hz and 20,000 Hz. Full stop.
Then she won't have said that this one I want to transfer. I want to come out and do
Full stop. Any sound produced outside this range, any sound produced outside this range cannot be heard by a normal human being. And such sound is said to be ultrasonic. Yes, anybody that is normal, I know hear that sound. With the exception of okay. So such sound is said to be ultrasonic. Full stop. Ultrasonic sounds can be produced. Ultrasonic sound can be produced with the aid of electronic devices. With the aid of electronic devices. With the aid of electronic devices. And can also be produced by bats. By bats.
Okay.
Adam, bats. But Abi, she don't understand bats. She understand Adam. Bats, among other animals. Okay, batsman, Oma picking.
That's fine. I look like I enjoy.
So,
Batman. From Batman, you know Batman.
among other animals, full stop.
Batman, you know Batman.
It can be heard by dogs. It can be heard by dogs, cats. It can be heard by dogs, cats, etc. 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 Hello, Okpe. That's the last warning. You get out of this class.
Sorry, sir.
They can be heard by dogs, cats, etc. So ultrasonic sound ultrasonic sound found its application. Ultrasonic sound found its application in the medical laboratory. In the medical laboratory, where it is used in the study of fetal development.
Of what?
Fetal development. Fetus.
Okay.
Yes, fetal development.
The photo mix now. Mix now.
But like scan now.
He said, let me knock that boy.
It's not minutes now.
And the process is called ultrasound scanning. Yes, it's fetal development.
He's not developing, more of monitoring.
Development. What are you monitoring?
Like when you see
It's the development of the baby.
Development.
Yes.
We are taking development.
So that's why I was like, fetal. Okay, so that's English.
Ah.
We have our language.
Another subtopic, beats, 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 beats. Beats occurs, yes, beats,
You are not
B-E-A-T. Beat occurs when two notes. Beat occurs when two notes with slight difference in frequency. When two notes with slight difference in frequency are produced simultaneously. Are produced simultaneously. Full stop. The characteristics of wave that can result in a beat is what? Who can tell me? What character of wave can result into a beat?
vibration.
What character?
What's that?
I gave characteristics of wave. So which one can result in beat?
Okay, reflection.
Really?
It's echo now.
Is it Emmy reset his head. Yes, which character can result into beat? I want you to think. So will you stop there?
I'm thinking.
Yes, interference. I owe you money. I owe you money. So I'm going just start the money say you want to give me, and I'll give you. I owe you money. That's brilliant. Interference.
I'm thinking about that.
Interference. So the characteristics of wave that can result in a beat is the interference. Full stop. Beats can be used in determining in determining an unknown frequency of sound. Bits can be used in determining an unknown frequency of sound. Full stop. Also put this down. Bit frequency can be defined as the number of sound. Bit frequency can be defined as the number of sound heard per second. Bit frequency can be defined as the number of sound heard per second. Full stop. It is the difference between the two frequencies involved. It is the difference between the two frequencies involved. So, for unknown frequency, we have F2, which is equals F1 plus or minus the fundamental frequency. Oh, it's not fundamental frequency, it's bit frequency. Since we are looking for bit frequency, so F1 is the known frequency where then F is the bit frequency. Is there any question? Now take down this. From this now, how do you calculate the bit frequency? Find the bit frequency. I take down this question. Find the bit frequency. Find the bit frequency. If F1 is given as 208 Hertz, it's not Formula 1 or F1. Then F2 is given as 204 Hertz. Find the bit frequency. 204 Hertz. Find the bit frequency. Yes, what's the answer? So from here now, you can say bit frequency F is equals F2 minus F1. Abi? And what's our F2? 208 Hertz minus Abi? What's our F2? 204 Abi? 204. Remember, this one is carrying plus or minus. So we have minus F is equal to 204 minus what? 208. So minus F is equals minus 4. So F is equals 4 Hertz. Is there any question? Any question? Any question? Any question? I'm asking now. Any question? Because by the time I'll be asking question now. Any question? All right.
So, how do we put it? How would it make is minus f of plus f?
This guy, it's depending on what you are looking for actually.
So, what do we put 208 minus 204? Is this going to be minus f or plus f?
It's going to be plus. Because the answer must always be positive. The answer must always be positive. So if you're having a negative answer, remember that this guy is carrying plus or minus, and minus cannot stand ordinarily. It will what? It will tag along with the what? With the integer in front. Are we together? You cannot have a negative frequency now. Can't have. It's more like you are saying, okay, you can have acceleration and deceleration. Can you have a negative height? Do you get now?
So I'm saying they cannot hear it. So I'm saying
We'll fix that soon. Those of you watching us live, we'll fix it soon. Hello? Yes, sir. Is there any question? Any question? So that's the advantage of those that are in the physical class. Network cannot affect you. Okay. Alright, moving on, we're going to be talking about overtones of a vibrating string. Overtones of a vibrating string. So we are done with speed of sound and ultrasound and the likes. So this is where the work is. Someone brought some set of questions to me the last class, and I told the person that we are treating it today. Now the person is not here. You know that boy? The tall boy. The tall boy. I think he is a brother also. Your friend now. Your friend.
Please, kindly manage with us for now. We just have to on the generator. If not, everything you are saying will just disappear. God bless you. Manage, don't worry. You will do well. Just listen. Read subtitles if it is possible. After this live class, the video will be made available. So just make sure that you endure for now. God bless you.
Alright, moving on. Overtones of a vibrating string. Overtones of a vibrating string. Overtones of a vibrating string. So I'll be drawing a diagram for you guys. So I want you to Pay attention. So we have harmonics. It's more like a table, not a diagram. It's more like a table. Waveform, length, frequency, overtone. So this is the first harmonics, second, third, and fourth. So the waveform is like this. We have this and this. So moving like this. So from here to here is what? What did I tell you guys last class? One full circle is what? One full circle like this. One circle like this is what? Thank you. Lambda over 2. Lambda, not pi. Lambda over 2. So this guy is what? Is equals lambda over 2. So from here you can say what? Lambda is equals what? 2L naught. Now the L naught is the what? Original length. Original what? Length. So from here you can say the fundamental frequency will be equals, remember from the beginning, or let me say from the beginning, we have V to be equal to what? Yes, I said that on purpose. V is equal to what? F lambda, right? So making F the subject, what do we have? F is equal to what? V over lambda. So now since we already know lambda is what? 2L naught, we can say F is equal to what? Lambda V over 2L naught. From here, F is equal to what? V over lambda, right? And we already know that lambda is what? 2L naught. I mean, so we say F is equals V over 2L naught. And this is the what? Fundamental note. Fundamental note. Then the second harmonics, we have something like this. So this side, we have this and this. So we can see this and this. So from here to this place, say it is what? L1. And a complete circle is giving us what? A complete cycle is what? Everybody stand up. Stand up, stand up. Stand up. A complete wave cycle gives what? Oh, really?
3 lambda over.
Distance of one crest to another is what? Lambda. Then a complete circle will give us what? Lambda. Sit down, sit down. So L1 here will now be equals what? Lambda, right? L1 here will be equals lambda. So from this now we can deduce that our F1 will be what? V over L1. Lambda is already what? L1, Abby? So we can say F is equals, and this now can also be written as F1 is equals to F naught. Am I wrong? You are not even checking it. I said F1 is equals to F naught. How?
Because just like the first one, V over 2 L naught. So V over L naught equals to 2 L naught.
Alright, F1 is equals V over what? L1, Abby? And we said F1 is equals to F naught. What is F naught? V over what? 2 L naught. So 2 can cancel 2. So we still have V over L. Do you get that now? So that is that. Is there any question? Any question so far? So for this now, this is the first overtone. This is the first overtone. Now the third harmonics. We have something like this. So we can say 1, 2, 3. Are we together? So this now, from here to here, we have L2. So this side, L2. Abby? L2. So we can say, how many lambda is there now? How?
Like that first one, we have lambda over 2, then second one lambda. So lambda plus lambda over 2 equals 3 lambda over 2.
Brilliant. So, I won't chop my money today. No problem. It's more like you are saying 1 plus 1 over 2. And this is 2 over 2 plus 1 over 2. Which is what? 3 over 2. Having? So that's why we are having L2 to be equals 3 over 2 lambda. Or you can say 3 lambda over 2. It's still the same thing. Are we together? Are we together? Now from here, how do we make lambda the subject of the formula? Let's write, we say 3 lambda over 2. 3 lambda over 2. So making lambda the subject of formula, we cross multiply, we say 2L2 is equal to 3 lambda. So lambda will now be equal to 2L2 over 3. Is there any question? Ask your question. What I did here was to divide both sides by 3. If you divide both sides by 3 here, this one cancels this one. So we have lambda is equal to 2L2 over 3. Is there any question? Any question so far, please? Yes? Any question? The guy in blue. Any question? Those of you at the back. Any question? Hey. Okay. Oh. Alright. From here we can say our F2 will now be what? F2 will now be what? V all over what? 2L2 over 3, Abby. So if you write, what do we have? F2 is equals 3V over 2L2. Any question? I said L2 is 3 lambda over 2. And from here we made lambda the subject of the formula. Once you make lambda the subject of the formula, it will be what? Lambda is equals 2L2 all over 3, right? Now, remember that F is equals V over lambda from the original equation, which is V is equals F lambda, Abby. Then F is equals to V over lambda. Now we already know that lambda is what? 2L2 over 3, right? So we input here. And once you input here, this 3 comes up, comes multiplication. So you have F2 is equals 3V all over 2L2. Am I too fast? Are we on the same page? Are we on the same page? Gifts. All right. So we can also deduce that F2 is what? F2 is equals 3F naught, and this is what? Second overtone. Do you agree with this? F2 is equals 3F naught. Do you agree? Okay. Do you agree? Please put on your glasses. Please put on your glasses. I'm not used to seeing your face like this. Put on your glasses. Thank you. Yeah, do the calculation. Substitute F naught in that formula. F naught is what? V over 2L naught, Abby. So what do you have? Isale. Okay, Isale. Are we together? This aspect of sound used to come out very well. That's why I'm taking my time. You see, I never rush. I do it one after the other. Any question? Now let's move to the last one. So you can draw this last one. What would the waveform be like? How many are we having? 4. Correct. So draw that. We have something like this. 1, 2, 3. So this also form like this. 1, 2, 3. Don't mind my uneven wave. Just, you know when they say lebe, lebe. So one of my guy, when we were in university, he just say lebe kudek babe. I think we were talking about oxidization of fatty acid. You guys that are going for medical courses, prepare yourself for all this pathway of fatty acid metabolism, glycolysis, all these things. You will do it. Medical biochemistry, you can't escape it. So we're asking the guy, he was teaching us, he was explaining yesterday. I said, which method is it? He says, since that day, he started calling it Babe method. So this one now, you will what? Leve. Alright, moving on, we have this to be L3. So what will our lambda be? Alright, so L3 is equal to what? 2 lambda, Abi? Now make lambda the subject, divide by 2. Lambda is equal to what? L3 all over 2. Right? So now our F3 will be what? V all over L3 all over 2. So our F3 is now equals 2V all over L3. And this will be your what? This will be your what? Third overtone. So your fourth harmonics is your third overtone. They might ask you, what is the second harmonic? It is your what? First overtone. And your first harmonic is your what? The fundamental note. Keep that in mind. And this is the whole journey for overtones of a vibrating string. Good evening, sir. Sir. So this is the whole journey for overtones of a vibrating string. So now we'll take overtones of an open pipe. What have I mentioned about open pipe? Yes? Open pipes. Anybody? I said something about closed and open pipes. Yes? Open pipes. Oh yeah, look at this now. This and this. Which one is closed? Which one is open? Yeah, so when I ask open pipe, why are you looking at it like a fish? No, it's not the way. Just tell me something about open pipes. And that's it. Alright, so the next one is overtones of an open pipe. 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 So I'm not going to claim, so because we'll be using the table, let me just make some little adjustment. So I'll just edit. Hope we are done with the table. Are we all done with the table? Alright. Right. So moving on now. Overtones of an open pipe. So the first wave will be in this format. The first waveform will be in this format. We have something like this and like this. So we have something like this. So this is the first waveform, and we have our L naught, and we have this. So now, what is the lambda here? Hello, what is the lambda here? We have something like this and something like this. Hello, look up. We have something like this and something like this. What's the lambda? What's the wavelength? We have a quarter cycle twice. So we have what? Lambda over 2. Correct. Because half of this and half of this will give full, Abby. So this one will be what? Lambda over 4, and this is also lambda over 4, Abby. So once you sum this up, we have 4 lambda. Wait, LCM is 4. This in this, we have lambda plus lambda. So we have 2 lambda over 4. 2 here 1, 2 here 2. This is lambda over 2. Do you understand that now? Abby? So here now we can say L naught is equal to what? Lambda over 2. Make lambda the subject. We have lambda is equal to 2L naught, right? Hello? And the frequency, which is the fundamental note, to be what? V all over what? 2L naught. Any question? The next waveform will be something like this. This is the next waveform, and this is our L1. This is L1. L1. And this is L1. How many lambda is here? 1 lambda. So our L naught is equals lambda. So our F1, sorry, this is L1. Our L1 is equals lambda, and F1 is equals to V over L1. Any question? Any question? Any question? Any question? Now transfer all the information for that of it. F1. F1 is 2 F naught. F naught. So transfer all the previous information for this. For this. The one we got for vibrating string, transfer it for this. For the length and frequency, let me give you the waveform. the last one. This is L2. So if you look at it, this one is already resembling what the previous one we did, Abby, in terms of the length and frequency. So this one now, F1 is equals to F0. So you just transfer the information for it. Then we do that of overtones of a closed pipe. Then we take 1 or 2 switch questions, and we're done for the day. This is vibrating string, not close pipe. Vibrating string. Correct. F3 is same as 4F0. The next one, overtones of a closed pipe. So it's this one that is a little bit odd. Overtones of a closed pipe. Overtones of a closed pipe. Are we done?
I think equals to 2F.
Yes, it is. F3 is equals 4F naught, not 2F naught. F3 equals 4F naught. Then F2 is equals 3F naught. Solve it properly. F3 is equals 4F naught, F2 equals 3F naught, and F1 equals 2F naught. That's the standard. F3 now. F3 is what? 2V over what? L3, Abby. So we said F3 is equals to 4F naught. What's F naught? Over what? 2 here 1, 2 here. F3 is equals to 2V over what? Hope we are together now. All right. Any questions so far? Any questions so far? Any questions so far? Any questions so far? Please respond. Now, overtones of a closed pipe. Overtones of a closed pipe. The first waveform is this. This is the first waveform. So we have this to be the L naught. So what's the waveform? What's the wavelength here? What is the wavelength here? Lambda over 4. Thank you. So our L naught here is totally different. We have lambda over 4. Making lambda the subject, we have what? Lambda is equal to 4 L naught, Abby. And our frequency, stop writing, no, pay attention. Someone should refill this. Thank you. Yeah, get under my camera. Yeah, fast. I use the pencil. Okay. Or debate. Alright. So from here we can use the F is what? V over 4L naught, not 4 lambda. So the next one, the next waveform, we have something like this, closed pipe. We have something like this. Then we have this. So we have L1 we equals this. So this is L1. So how many wavelengths can we remove from this now? From this waveform? Are you sure? Look at it again.
Yes. No,
3 lambda over 2 because we have lambda over 2 and lambda over 4. Abby? So we have lambda over 2 plus lambda over 4. And what's this now? We have 4. So in this we have the 2 lambda plus lambda, which was 3 lambda over 4. Are we together? So L1 is now equal to what? 3 lambda over 4. Making lambda the subject, we have 4L1 is equal to 3 lambda. We have it by 3. Lambda is now equal to what? 4L1 over 3. So getting to this place now, F1 will now be equal to what? 3V over 4L1. Any question? Any question? Any question?
the fundamental note is half. The second one not meant to be the second half.
Now, this what's it called? For closed pipe, you have odd integers. Odd integers. If you should look at it now, you can say F1 is equals 3F naught. Check this. F1 is equals 3F naught. Abby? So this now, instead of even integers, you have odd integers. Do you get that now? So that's the only difference. But for waves in Overtones in vibrating string and that of open pipe, they are the same thing. Closed pipe is the only odd head. Are we together? Are we together?
Yes.
Alright. So the next one, the waveform is this. This is what the waveform looks like, and you have this L2. Yes, from here, what is our lambda? L2 equals, are you sure? This and this is 1, Abby? Plus half, that is 3 over 2. Very correct. So we have 3 lambda over 2. So our this thing for lambda, we have 2L2 is equals 3 lambda divided by 3. So lambda is equals to what? 2L2 all over 3. So our F2 now will be what? 3V all over 2L2. And what is that? So our F2 is equals 5 F0. Like I said, odd integer, odd integer. You don't understand? You don't understand? What's 5 lambda over?
Lambda plus lambda over 4 is 5 lambda over 4. Not 3 lambda over 2.
Okay, this is not 1 over 2, it is 1 over 4. So we have what? We have 1 plus 1 over 4, which is what? 5 over 4. So this, you give us the wrong answer. Someone should find out. Find a fine. So this is 5 lambda over 4. Sorry for that. This is 5 lambda over 4, right? So this is 4 over 5. Abby? So this is 4 lambda over 5. So this is 5 over 4L2. 5 over 4L2. So are we on the same page now? Alright, so moving on. We have this. So this should be like this. So we have L3. This is L3. So from here, how many lambda do we have? If you say anything again, please let me prepare that mop stick for her only.
I got to say
Not me. This is what? Over 2 over 2. This is 1. And this is 3 over 2 lambda. So we have 3 over 2 plus 1 over 4. LCM is what? 4. 6 plus 1, which is what? 7 over 4. See what? So L3 is equal to what? 7 lambda over 4. So we can say 4L3 is equal to 7 lambda. Divide by 7, divide by 7. So lambda is equal to 4L3 over 7. Abi? So our F3 now will now be equal to what? 7V over what? 4L3. And this F3 is what? 7F0. Abi? So these are the overtones for closed, open, and vibrating strings. So once you are done with that, let's take questions. Calculation. Are we together? Can we proceed forward? Are we done with the table? Alright, JAMB question, which is UTME question, 1998, question 27. UTME question 1998, question 27. Question 27. Are we good to go? Are we good to go? A steel wire, a steel wire, a steel wire, a steel wire, steel wire, a steel wire, a steel wire, a steel wire of length, a steel wire of length 0.50 meter, a steel wire of length 0.0 meter is stretched between two fixed points, is stretched between two fixed points, and its fundamental frequency is 200 Hz, and its fundamental frequency is 200 Hz, full stop. The speed of the wave in the wire is how do you tackle that question? Yes. Can I help you, sir? All right. So what were the parameters given? Which length? L naught, thank you. 0.50 meters. Yes, what else? Fundamental frequency is what? 200 Hz. What are we looking for? V. Now, looking at this, what is the formula for fundamental frequency? In which one are we using? Thank you, vibrating string. Fundamental frequency F naught is given as what? V over 2L naught. Some people will go and use V over lambda and they will get rubbish. And JAMB will do it on purpose. They'll put the answer for what? V over lambda there. So anyone that did V over lambda thinking it's correct will pick the wrong answer. Why the original formula is F is equals to what? V over 2L naught. Please take note. So from here we can say that if we make V the subject of the formula, what do we have? So we have what? V is equals F naught to L naught. You can say V is equals to F naught L naught, which is now equals 2 times what? 200 times what? 0.5. And this one is what? 0.5 is what? Convert to fraction. 1 over 2. 2 cancel 2. So our velocity is what? 200 what? Meter per second. As simple as ABC. As simple as 1, 2, 3. Any question? Any question? So against next class, go and search your JAMB past question and bring out questions similar to this. Questions on overtones of closed pipe, open pipe, and vibrating string. Is that clear? Now let's take down the second question. UTME question 28, 1998. UTME 1998, question 28. UTME 1998, question 28. Are we good to go? In a resonance tube experiment, in a resonance tube experiment, if the fundamental frequency of the vibrating air column is 280 Hz. The frequency of the third overtone is which formula are we using? Which of the overtone are we using? In a resonance tube experiment, pipe is being used. Thank you, closed pipe. So we are using closed pipe. So what are we doing? What are we doing? F naught is what? 280 hertz. I remember, what's the relationship between third overtone and this one and F naught? Is 7 what? F naught. So you just multiply 7 with 280. What do we have? What do we have? 1960 hertz, 9060 hertz. 1960 hertz. So take down this quick sweet question, a very sweet question. This is assignment 2. Assignment 2. Assignment. Assignment. The fundamental notes. The fundamental notes. The fundamental notes. The fundamental notes produced in a closed pipe. The fundamental notes produced in a closed pipe of frequency 80 hertz. Of frequency 80 hertz. Full stop. How many overtones? How many overtones? How many overtones? How many overtones are there? How many overtones are there? Between 100 hertz, between 100 hertz and 700 hertz. Between 100 hertz and 700 hertz. For those of you following us on live, please subscribe, like and share. So this is where we call it a day for today. So have a good evening, guys.
Seven times.